The image is simple and known. A beam of light enters a glass of water and bends. This phenomenon, which is learned at school, is a demonstration of refraction. However, behind this apparent simplicity is hidden a question that has puzzled generations of physicists. How much momentum does light actually carry when entering into a material such as water or glass? If you are interested in this topic, don't forget to subscribe and like this video. The answer to this question has divided the scientific community for over 100 years between two opposing theories, that of Abraham's impulse and that of Minkowski's drive. Recently, a new study proposes a solution that combines both perspectives in an innovative way. Physicist Adam B. Cahaya holds that the behavior of the light spin, an essential quantum property, allows reconciliation of both visions. This new approach facilitates the understanding of how light transfers its linear moment by interacting with matter. Thus, theories that seemed opposite can be integrated into a single broader explanation. The root of the problem lies in the fact that when entering a medium such as glass or water, light slows down and changes direction. This creates a fundamental doubt. Does that change mean that light gains or loses momentum? Minkowski states that light gains momentum, while Abraham defends that it loses it. Both theories are grounded, but offer contradictory results. The new study does not invalidate any of the theories. Instead, it integrates them into a more coherent explanation. To do this, it relies on the quantum concept of the spin, which represents the inner rotation of the particles. According to Cahaya, Minkowski's impulse refers to the magnitude of the moment projected on the spin, while Abraham's is related to the expected value when interacting with matter. This approach makes it possible to interpret each type of impulse as a distinct phase from the same physical phenomenon. The distinction between the concepts of Abraham and Minkowski becomes key to resolving the conflict without discarding previous contributions. Thus, light becomes an even more fascinating and complex object of study. The spin is not a physical twist in space, but a quantum property that determines the behavior of light. Cahaya develops a model that incorporates the spin in the equations of the propagation of light in dielectric media, using a formulation inspired by the Dirac equation, which describes relativistic particles as the electron. When applying this idea to light, there are two components: the electromagnetic wave with right polarization and that of left polarization. These components interact thanks to oscillations in the material, generating an oscillatory phenomenon known as Zitterbewegung. This tremor of light suggests that its behavior cannot be understood without considering its internal quantum structure. Cahaya's work develops a theoretical framework that combines the electromagnetic field with the response of the medium. One of his key predictions is that Minkowski's impulse can be derived from the diagonalization of the Hamiltonian system. This implies that Minkowski's value describes the path that light will follow when passing through a medium. On the other hand, Abraham's impulse appears when analyzing the net effect of light on the medium. Cahaya demonstrates that the average value of the moment projected on the spin reproduces exactly the formula of Abraham's impulse. Thus, both values emerge from the same physical system, reflecting different facets of the phenomenon. Although it is a theoretical work, Cahaya proposes ways to detect predicted effects. For example, optical Zitterbewegung could be seen through the movement of wave packages in structured media. This approach could have implications for technologies that require precise control of light, such as photon materials and quantum computing. The importance of spin is not only technical, but offers a new perspective on an old problem. Instead of seeking a unique answer, Cahaya integrates the two existing approaches, showing that both are valid in their context. Thus, light is revealed as an entity with both undulating and corpuscular characteristics, showing its dual nature.